My name is Jimmy. I'm a part of the management team, head of software, and also a system engineer in APTAS. So APTAS is a 1U CubeSat. So what is a CubeSat? A CubeSat is a small satellite with fixed dimensions. The smallest type is a 1 unit, which is a 10 by 10 by 10 cubic centimeter box. As can be seen in the image to the right, a 2-unit CubeSat would be the same size as two 1-unit CubeSats stacked on top of each other. The largest CubeSats today are up to 27U. There are many advantages to designing using the CubeSat standard, namely that components are off the shelf, meaning they are cheaper, fast to develop, and standardized. Additionally, there is already a market built up around designing and launching. Let's begin with a small mission overview. APTAS is an acronym for Atmospheric Polar Transmission Alignment Satellite. It's named after the mountain Aptasvara that's located behind campus. The mission will be carried over an expected lifetime of 6 months. The fully student-developed mission will carry 2 payloads on board with the following mission objectives. The first payload, the ECAT payload, aims to support the calibration of the ASCAT 3D antenna arrays, and the second payload is a camera which will take images of Earth and aim to monitor changes of glaciers over time. Furthermore, the mission will provide hands-on space experience and operation experience to students at Space Campus in Kiruna and provide a starting point for future CubeSat projects at LTU. We hope to be launching at the summer of 2022. So satellites are usually divided into payload and support platform. The payloads are the reason we send satellites into space. It's the sensors and devices we want to operate and gather data from. The support platform is everything needed to run and use the payload, such as the computer, electrical power system, control system, and so on. The subsystem teams in APTAS can be seen here on the right, and we will go over each subsystem in a bit more detail in the coming slides. First is the science team, utilizing the camera payload. The main use of the camera is to track glaciers, but can also scout for other interesting activities. On the image to the right, there are 3 happy APTAS members taking a selfie with the camera. As you can see, a camera made for over 300 kilometer altitude has some focusing issues when used point blank. The electronic design team are the subsystem that designed and built all of APTAS custom PCBs. APTAS uses 3 PCBs, the ECAT payload. It's made to output a sinusoidal 233 megahertz signal of 60 milliwatts. The signal will be received by ASCAT 3D as a calibration signal. The umbilical board is a very common board when designing satellites. Once the satellite has been assembled, you're not allowed to disassemble it again. If you do, you run the risk of damaging components or having connection troubles. So if you disassemble it, you have to redo all the tests you've done to confirm that it still operates as intended. The umbilical board is the interface between the engineers and every pin needed within the satellite when it is assembled. The step-up board is a small board that reroutes pins and solves another problem, which I can point out later when I show a picture of the entire satellite. The mechanical team is in charge of testing the CubeSat to ensure that it is ready for launch. This will include mechanical tests such as random vibration, quadratic, and shock tests for our custom PCBs that's shown in the picture. So far, random vibration and quadratic testing has been performed for the ECAT payload board, which passed both tests. The entire APTAS system will be protoflight tested into a test pod prior to launch. The launch provider requires only random vibration testing to accept the payload for launch. However, both quadratic and shock testing will be performed based on availability and will provide a learning experience for the students to better understand the launch loads that payloads experience. Additionally, thermal testing will be performed in 2 thermal vacuum chambers on campus. First, component bakeout will be performed. This is a procedure to remove volatile compounds that easily escapes the materials on the vacuum. When this happens in space, it's called outgassing, and this can lead to circuit shortings and other troubles with sensors and electronics. The boards will undergo this bake-out prior to integration within the overall system. After the test, the total mass loss will be measured. If it is low enough, it is qualified to launch. Second are thermal cycling tests. These are done to ensure that the satellite will be functioning after experiencing the large thermal variations that it will undergo in orbit. All components are pre-selected to be able to work within the expected temperature range of the orbit. A requirement for testing is to conduct operational tests under these thermal conditions. A satellite needs some sort of attitude determination and control system. The attitude determination will determine our current orientation. If the camera is going to take a picture of Earth, we would like to know that it's actually pointing towards Earth and not the sun. For attitude determination, APTAS will use a gyroscope, magnetometers, as well as the solar panels housing 4 core sun sensors on each plus-minus X and Y panel. These are used to triangulate a sun vector. For control, our satellite will use magnetorquers. These control the satellite by creating a magnetic field, which in interaction with Earth's magnetic field creates a torque. As APTAS has no reaction wheel, we will not be able to point, but rather use the control to try and decrease the rotation as far as possible to enable operations of the payloads. APTAS has 5 operating modes. Upon boot, we will go into a deployment mode used to deploy the antennas. We have a charging mode, so if the battery state of charge falls too low, it's a safety mode. A nominal mode where the satellite waits for commands, and 2 payload modes in which we will operate the payloads. The satellite will use I2C and CAN bus for communication between components. The CAN bus is only used between the onboard computer and the camera payload to give a slightly higher data rate than the I2C bus can offer. Communication with ground will be covered on the next slide. The operators are controlling the satellite by sending commands. The commands can be combined with the flight planner to operate the satellite at specific places in orbit and start transfer to downlink data to ground. We will also continuously monitor the telemetry of the satellite. The communication team is responsible for the communication between ground station and satellite. The team has designed and are currently setting up the ground station in the building of Kiruna campus. A lot of work has been put into getting the communication between satellite and the ground station working, and the 9th of July this year, we finally got it. The image here is our first fully correct decoded beacon. On this slide, you can see the layers we use for communication. If any of them say anything at all to you, please send in your application. In this image, you can see the configuration design of APTAS. Around this configuration, there will be a structure and then solar panels. Starting at the bottom, we have the antenna module. It's 2 dipole antennas. One will be used for communication with ground, with the other being used by the ECAT calibration payload. On top of this, we have the motherboard with both the onboard computer and the transceiver. It's a really compact design, having both of these components on one board instead of using 2. Close to the middle, we put the electrical power system. As this is the heaviest component, it won't move the center of mass too far from the center of the satellite. After the EPS to the left, we can see this step-up board I mentioned earlier. This board is used to make the stack running through the entire satellite a little bit smaller so that it can fit in between the camera legs, and also raise the stack so that it reaches the next board. The camera is a 5.7 centimeter tall, which makes it 57% of the entire satellite. As we were going to use another payload, we needed to be creative and make a hole in the boards. This allowed us to fit both the ECAT payload and the umbilical board in the satellite, really making use of every bit of volume that we have. Thank you for listening to this presentation, and I look forward to your application. I also forgot to add all the social media platforms, but we also exist on Instagram and Facebook and LinkedIn, so please go in and follow us there. And as I am not on campus today, I can answer questions in the YouTube chat, or you can just send me an email. if you need my mail, just ask Kira or Adam or somebody there, and they can give you my mail. Thank you.